Hello, my name is Chris Johnson and this is my video for Lab 2, Motion of a Falling Object for Physics 2211. We will begin with the tracker setup and observed motion of the falling object, followed by the computational model analysis and the related physics concepts. To conclude, I will compare and evaluate the models to the actual observations, as well as answer the what-if questions and provide any final critiques. In this lab, I'll be comparing the observed motion of the falling object to a model with gravitational force acting on the ball and a model with both gravitational and drag forces acting on the ball. I will use these predictions to observe the nature of terminal velocity and the outside forces which affect falling objects. I must first analyze the ball's actual motion via tracker. To begin, I set the point of origin of my graph, calibrate the distance parameters by setting the diameter of the ping pong ball to a measured 0.038 meters, and take note of the start and end clips. For each frame in this range, I track the average position of the ball, which is in the center. It is worth noting I needed to slightly shift the axis by a -1/7 of a degree due to the nature of the video. I took the data on the right side of the screen and moved it to Excel to observe the ball's change in position over time. We can see that the change in position over time, or velocity, is not constant, so our ball must be accelerating due to a net force being present. From Newton's second law, we know that if a mass is constant and acceleration is present, then a net force is acting on the system. What force or forces are acting on our system? Let's test if it is the force of gravity alone, or the mass of the ball times the acceleration of gravity. Let's model the force of gravity on the ball using a computational model. To begin, I must first make some initializations. First, the mass of the ping pong ball is 0.0027 kilograms. I set the original position of velocity vectors to x0, y0, z0 because the object begins at rest. I set the appropriate times as well as the force of gravity. The equations we need to construct this model are the force of gravity on an object, which is equal to its mass times the force of gravity, multiplied by the unit vector for the y direction to convert it to a scalar quantity. Then we can continuously update the velocity by taking the previous velocity and adding it to the acceleration, or the force of gravity over mass, multiplied by time. With the final velocity, we can use the position update formula to update the position through every iteration. In code form, we create a loop to update velocity every time step, or every 0.001 seconds, as a result of the force of gravity acting on the ball. We can use each updated velocity to update the position of the ball every iteration as well. Once I run the code, I see a similar graph to my observed and move the data to Excel to compare this model to the observed data. It is clear the model overpredicts the position of the ball, so there must be another force acting in the opposite direction of gravity, slowing down the ball. Let's build a model including turbulent drag force to explain this discrepancy. Turbulent drag force is proportional to the square of the ball's velocity. To code this in GlowScript, I must first make some initializations. First, use the norm function to find the unit vector of the ball's velocity. This is important because we need to use the unit vector to convert our velocity to speed, because you cannot square a vector, but you can square a scalar. In line 73, I perform the calculation which is equal to the formula of turbulent drag force. Then we add this against the force of gravity as it acts in the opposite direction. In this lab, we must fit the proportionality constant so the model's final position matches the final observed position to ensure a correct drag force. After a couple of iterations changing the b-value, I found that 0.00038 was the value that fit this model. As you can see, the model's y-value and the observed y-value are almost exactly the same. The output of this code visualized the vector forces acting on the ball. We will go more into depth of the information that tells us this later. I moved this model's data to Excel. Because we had to match the final values to find an accurate drag force, the emphasis is on the predictions within the blue lines. Although it is very small, the gravity and drag force models slightly overshoot the distance again. To answer the what does it mean question, none of these models predicted terminal velocity during the observed time. Because an increase in velocity results in an increase in drag force, there will be eventually a point where the drag force equals the force of gravity. At the point the ball reaches terminal velocity, the net force is 0 because the drag force equals the gravitational force in the opposite direction, and the object stops accelerating and moves at a constant velocity. Terminal velocity is impossible without drag force, so the only model which could have a terminal velocity is the last model. After looking at the force vectors on our model, drag force was present, but the force was not present for long enough to reach terminal velocity. If given enough time, it would reach terminal velocity. To answer the what-if question, we must adjust our code to give the ball an initial velocity. Due to the increased velocity having a positive effect on drag force according to the drag force formula, we should see a greater drag force across the same period of time. Our free body diagram confirms this, and although terminal velocity is not reached in this time period, it would hypothetically reach it much sooner in this scenario over a longer time period. For a final critique, I believe this small difference in gravity plus drag model in the observed was the initialized weight of the ping pong ball. I did not have a scale to weigh the ping pong ball, so I used data from the internet to record the mass. This very small difference could be the reason why there is a small difference between the model and the observed data. Thank you for watching my video lab report on Lab 2, Motion of a Falling Object. The link to my GlowScript code is in the video description.